Hey, Professor Lewis here, and we're going to be talking about welding calculations for bending applications. Now, we've already learned a little bit about weld callouts and weld sizes and the processes and just a simple shear application of a weld. And that one we use the simple stress equal force over area because we were using it across that effective throat area. And let's just do a quick review of some of our statics and strengths fundamentals here, and before we get into the equations that we're going to be using, and this will be a good base layer for us to remember. We're going to use stress as force over area. That's axial loaded type member, so something like in a tensile force, we're applying that force across this area evenly. Now shear, we would be applying the force in the other direction and going across there, and we're going to be talking about that in a little bit. A lot of times we reference this as normal stresses. Okay, we have the bending stress, which is MC over I. And if we think about having a simply supported beam, now let's think this is a round beam here, and we have a force in the middle at some distance, and I've exaggerated it bending. We're going to have the tendency to the bottom of the beam being in tensile, the top of the beam being in compression. Somewhere we're going to have a neutral axis on that member, and if it was a round piece, it would be about the center of that. That would be the distance, C would be the distance to the max stress in tensile or compression for that member. And like I said, this is all water under the bridge for you guys. And you can remember, you can figure out this M right here, the max bending moment, by the location here. Now, what X would I use? We came down and remember you guys did beam diagrams where you did the shear and the bending moment diagrams right here. And we could figure out the max moment. And for this problem, the max moment would be right here. So we would want to calculate the maximum stress at that value. Now this has an I on here. You guys know that's the second moment area from inertia, and we can come in here and calculate that sectional property of that material, and we would have to match it up. This is I value for a circle, so a square is like BH cubed over 12 for a square. And that kind of finishes up a little bit about what you guys learned in strengths. And we're going to apply a lot of the same thought process to a weld. In a weld, typically we have one member going in opposite directions of the other member. So we have these two pieces not connected right here, but connected through a weld, and the weld's going to have an even leg on this side and this side. And if we use basic trig, we can calculate that this is going to be a 45-degree angle, which if we take the sine or cosine of that, that is going to be 0.707 over here. That's going to let us get the effective throat on this. Now if we want the area, we're going to have to take the throat times the length of the weld to get the effective weld area. That's really important for us to calculate the stress across that weld. That's where we'd like to see it fail. Now, if we don't do a good job of weld prep and remove the oxides off the metal, we may not get good diffusion and fusion welding into the base materials and good penetration. And so that could limit the problem, and we can actually have the welds basically, it's almost like it just delaminates right off the metal. So let's take our basic equations, force over area, MC over I, and let's look at it in terms of shear stress for bending. And this is, we're going to be doing this formula in lab. So I'm just going to reference this as tau prime and our secondary tau right here. So primary stress, secondary stress. And this is going to be across the weld. Okay, so we need to take the length of the throat, times that throat distance there, and we can get that effective area. And we can put that in here, put our force on there. We got primary stress, pretty easy. Secondary stress, we need to calculate the M, the max moment, our C, the distance from the neutral axis, and then our I value. Now let's do a quick review a little bit about strengths or material science here, and see if I can get this on the screen here where it stays on there and get everything in the window here. We talk about stress strain diagrams, and stress we can plot on this axis is typically in PSI. Strain usually is unitless, but it's an inch per inch. A lot of times we reference that, but that's the change in length versus the original length. And what we're going to do is do a plot. And now when we go in the lab and we do our testing, you are going to see a plot on the screen, and it's probably going to look very similar to a stress strain diagram, but it's going to be load and deformation based off the stroke of the machine. And what we can see on a true stress strain diagram is there's going to be a linear region. You guys know that. We call that Hooke's laws applies, modulus elasticity. If we can't see the definite yield point in the material science course, we put an offset rule on and we can establish that. But here I could probably tell it's going to be right here, and that's where we design all of our parts to be used in applications, is below the yield strength, so that we can load it, unload it, and it's not plastically deformed. It's like a rubber band. It's elastic. Now there's a UTS, the ultimate tensile strength. That's where we're really going to see a lot of deformation, and we're about to the highest load that that point that part's going to take. Now all this is based off of normal stress, where we're pulling axially. Now if we put a shear stress across that area, we're going to have to bring in the deformation, the change of shear values. We can't take the UTS value and apply it to shear stress directly. We're going to have to use something like the distortion theory, where we take 57.7% times that value, and we can get the shear strength of that material. So you need to remember this right here, because we're talking about shear. And we're not going to find published data on shear values, only UTS and yield. Okay, let's look at a sample bending problem here. And I want you to use the same format for your calculations. I'm going to let you guys do this by hand and attach it to your lab sheet as an attachment. You need to have given, find, solution. Do your work really nice and neat. Use a ruler for drawing your lines. Don't freehand everything. We're going to be grading on neatness. And this is what you've learned in statics and strengths. I mean, guys, let's just apply it in lab and keep up good practices. Okay, here we have a problem where we have a plate made out of A36 steel. We have a round shaft, 1.5 inches in diameter, of A36 steel. And we're going to weld this part all here. Now, I can tell what kind of weld we're doing because we're doing all-around weld, 1/4 inch fillet weld on this part. We're going to use E70 wire. We know what that is from a previous lecture. We're going to put 900 pounds on here. Now, will it fail or will it not fail? That's what we're going to calculate and look at. And what we're asking here is, what is the worst weld stress that's going to happen? My solution is basically, I'm going to calculate my primary stress. Tau prime is force over area. Well, force is 900. That's pretty simple. But what area do I use? Okay, I need to use that effective area across that weld, but it's going around a circle. This is where we're going to not really try and dip into the heavy theory of what machine elements, machine science course is going to do, but we're just going to leverage a simple table out of their book that's going to be from table 9-2, and the book is Shigley's Mechanical Engineering Design. A lot of this theory is based off of, weld theory is based off of the Blodgett books, which is an excellent book. He references a lot of his stuff from them. But I'm just going to put the Shigley table in here, and you've got that in Canvas so you can download and read. It's kind of hard to read on this screen here. What we're going to have to do is go down through this table and find what looks like our weld here. And if I go down, I can see this looks like our weld. We're doing a circle, and it's about a point, and there's a radius. We can take that 1.5 inches and get 0.75. It tells me my area and my IU. Now the headers are right here. I went ahead and took that information and put it over here so we could see it a little bit better. Now this is talking about the throat area for that weld. Again, I'm going to have to take in consideration the length. Okay. The other thing we have here is this IU. This is our unit second moment of area. A unit, it's an IU value. It's to the 3rd power. Normally, I is to the 4th power. So we're going to have to learn how to convert IU to I a little bit later. And so that's not very hard to do. Since I have these wonderful equations, let's go ahead and populate them. And again, show your units in your calculations. I've got my area being calculated here. I've got my IU value because I know I'm going to need that value. So let's go ahead and calculate, and I underline those two numbers that I need. And let's go ahead and calculate our primary stress value. That's force over area. I can use this area right here, put that in there, and I've got 270 psi. Now we need to calculate our secondary stress. That's tau double prime, MC over I, not IU. So what we've got to do is convert our IU here to I. And So to do that, we're going to convert I by taking the throat distance, okay, times that IU value. So we know that 0.707, that's the sine or cosine of that angle, times the height of the weld, times that area. The effective is now going to be 0.242. We can calculate the moment. That's going to be at the wall we talked about, 900 times 3 inches. That's going to be our maximum moment. So we have everything we need right here to put in this equation. And that's what we did here. We populated it. C being the radius, the distance to our neutral axis there. And we got tau double prime. We're going to use von Mises type theory of combining stresses, where we say take tau prime squared plus tau double prime squared, take the square root of that, and that's going to yield our resultant shear stress, which we found right here. Now the question is, will this break? If we're using E70 rod, and we assume right now it's going to fall in the weld across the effective throat area. Now this E70 has a 70 KSI rating. We have to apply the distortion theory, 57.7%, and find out that the shear strength of this is only going to be about 40 KSI. Now, if I look at this, this is smaller than this. More than likely, our application here is not going to fail, but we found the worst weld stress in this application right here. Now, you guys are going to fail, so hopefully it fails at the weld, and you're going to be comparing the resultant stress with the strength of the weld in shear. So will it yield? Now, in a future course, you guys are going to be taking and learning more about the codes and how to apply the yield strength limits based on the type of joint, and there's a lot more theory there, and I'm not going to dive into that in this course. We're just wanting to look at the simple question of worst stress and did it fell across the weld. It's kind of a good segue to the machine elements machine design course down the road, and you need to be doing that kind of work later on, not in this course.